Hello again. So we are continuing on with the chemistry of life, and we're going to focus now on bonding. All right, so let me go ahead and try to figure out how to share my iPad again. Could take a second. I didn't realize you could see me the whole time in the corner there. Hello. Hopefully it doesn't block. I'll try not to write up there now that I realize that my face is just always there. Okay. So we left off here with atoms where you can either make bonds that are holding atoms of the same kind together, or you can have bonds that are holding atoms of different kinds of atoms together. Or you can have bonds that are holding ions together. All right. So chemical bonds hold atoms together in the molecule. And remember, chemical bonds form specifically when we are dealing with reactive atoms. And if you recall, reactive atoms means that they have unfilled, what are those called? Orbitals. Unfilled outer orbital. Unfilled outer orbital. Hopefully you can read that. Sorry. And we're talking about three main kinds of chemical bonds. We're talking about ionic bonds, covalent bonds, and hydrogen bonds. All right. And you should be familiar with these, or at least you should have heard about these from your chemistry classes. Right. So I'll go through all of them in particular. You might notice that there are some kind of bondings that are not talked about here, like van der Waals. They don't come up in biology that often. And so I'll mention them if they come up, but in general, these are the three that you need to know. This here is a great chart. Your book has great information about these, but I'm going to go through each of them. So ionic bonds, the most important thing about ionic bonds is that you are dealing with positive and negative ions being attracted to one another, all right? So let's look specifically at this sodium atom up here at the top, right? And let's look how many, what is its atomic number, right? So we can look at the number of protons. So we know its atomic number is 11. That means it has 11 protons and 11 electrons. And we can count those, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But what you'll notice is that there's only one in the outer shell. That is a very unstable molecule. It's not close to being filled. So what it wants to do is get rid of that ion. And so it's going to donate it to another atom. I think I said ion. Get rid of that electron. So it's going to donate it or give it away, right? So when that when that sodium atom, which is electrically neutral, gets rid of a negative charge, it becomes positively charged, right? And that is now a sodium ion, which is positively charged, right? If we look now at the chlorine atom, again, here it has 17 protons, meaning it has 17 electrons. So there's 2 in the inner shell, 8 in the second shell, and 7 in that outer shell. So we can look at them. 1, 2, 3, 4, 5, 6, 7. You notice that it is very close to being 8. It's very close to being happy. So what does it want? It wants to steal an electron from somebody else. Luckily, sodium, it has one you can steal from. So when it steals an electron, it's going to become more negative, right? It was electrically neutral, and now it's going to become a negative ion. An ion literally just means a charged atom, right? So sodium is now a positive ion. Chlorine is now a negative ion, sometimes called chloride now. All right, so when we have a positive sodium and a negative chloride now, they will attract through an ionic bond that will hold them together, all right? So ionic bonds are going to be holding ions together, right? And these actually get disrupted in water very often. So ionic bonds can be disrupted in water. All right. Okay, and we can see salt dissolving in water. All right. And we're going to have some practice ionic bonding, but we're going to save that for class time. Now we go on to covalent bonding, which is sharing electrons, all right? So we are sharing, I'm trying to put my face somewhere else, but I don't think I get a choice. Sharing electrons. Covalent bonding is strong like bull. It is very, very, they're strong. So covalent bonds are strong. You like my little bull there? Strong like bull. So the reason that they're really strong is that it involves two atoms coming together very close and sharing electrons. And when you're sharing electrons, you're basically bound together really tightly. So a reactive atom can be stabilized by sharing electrons from another one, and that's called a covalent bond. So two electrons, one from each atom, get shared in a covalent bond. So if we look here at this hydrogen atom, it has one proton, meaning it has one electron. How many electrons can fill that inner shell? It wants another one. So it's missing one. If we look at oxygen here, it has 8 protons and 8 electrons, 2 in the inner shell, 6 on the outer shell, meaning it can have 2 other electrons, right? So what happens when oxygen and water get together is that you form H2O, right? We're all familiar with H2O, water. You're gonna have a covalent bond here and a covalent bond here. And that is going to cause these to get very close together and share those electrons. I would like you to practice trying to draw water using your kind of electron or atom, what do you call it? Atom atomic, the way that we learn to draw them, right? So using these kinds of pictures, I want you to try to figure out how you can share those electrons. And we can go over that in class. So if you look at a lot of these atoms that are really important in biological molecules that we already talked about, carbon, hydrogen, nitrogen, sulfur, oxygen, didn't really talk about sulfur, but it's there. Here we have just a chart that shows you how many electrons are in their outer shell, or sorry, how many electrons are in their outer shell and what's the capacity of the outer shell. So that will allow you to figure out how many covalent bonds each of these really like to have, all right? So hydrogen likes to have 1 covalent bond. And we see that in water. Each hydrogen has 1 covalent bond. Carbon actually has 4 covalent bonds. Nitrogen 3, oxygen and sulfur are both 2, right? So again, carbon is super special. Carbon, special. And this is because it can do lots of bonding, lots of covalent bonding, and that gives it lots of kind of flexibility for making rings and chains and lots of different shapes. All right, let's see. All right, so covalent bonds, people get really confused with them about whether they're polar or nonpolar. So we'll go over that. So atoms within a molecule have different nuclear charges. And what I mean by nuclear charges are those protons in the nucleus, right? So the more protons you have, meaning the more positive charges that you have, the stronger the pull on nearby electrons will be, right? So if we look, for example, let's just look at this area here. This hydrogen atom has one, fluorine has 1, 2, 3, 4, 5, 6, 7. When they come together, they can kind of share and they're both happy then, all right? So atomic number for fluorine, 1, 2, 3, 4, 5. So that's gonna be 7 protons and 7 electrons, 7. And the charge of a fluorine atom, neutral. All atoms are neutral. All right, so what we can see is when we have this covalent bond between hydrogen and fluorine, that the fluorine molecule here is going to have so many positive charges in its nucleus is that it's going to pull the electrons towards it from the hydrogen, giving it a partial negative charge and the hydrogen a partial positive charge, right? That is polar. When you're polar, you get partial positive and partial negative charges. That usually has to do with atoms when they're two different atoms. A nonpolar is when you have two atoms of the same, right? Polar, different atoms. So really quickly, if we do our little water again, H2O, again, the oxygen is going to pull those electrons in, giving it a partial negative, and the hydrogens are going to be partial positive charge. All right. So again, if you have the same atoms, this is going to be nonpolar. If you have different atoms, this is going to be polar covalent bonds. The one exception that turns out to be very important is right here. Due to their very similar electronegativities, carbon and hydrogen have the same pull. Therefore, that is a nonpolar covalent bond, all right? So here, H's and H's, covalent, or sorry, nonpolar covalent. Also, CH, nonpolar covalent bond. Polar covalent bond is where you have different atoms giving you partial negative and partial positive charges. Covalent bonds can produce either nonpolar or polar molecules. So if you look at this whole molecule, now we're dealing with two different, you can see that there's a partial negative there and we have partial positives. That creates a polar molecule, all right? If, for example, we had something like this, because those are all non-polar covalent bonds, because C and H have equal pulling, this is going to be a non-polar molecule, right? Okay, I think that's good. We're gonna do practice with covalent bonding. Please do this, but we can go through this in class as well. All right, the last kind of bonding are hydrogen bonding. Hydrogen bonding, these are the weakest of the bonds. So they're very weak. However, they are collectively strong, right? So if you have a lot of them, it can be very strong. But one hydrogen bond, very weak, easy to pull apart. So hydrogen bonds are attractive forces between polar molecules. And in particular, what we're going to see is that it is between hydrogen and oxygen, hydrogen and nitrogen, and on very rare occasions, hydrogen and fluorine. Sorry, my son is coming in. Hydrogen and fluorine, but we don't see that very often. So really, the hydrogen bonding that we're going to see always involves a hydrogen. Nice. And then it also has oxygen or nitrogen, right? So these polar molecules, such as water, have partially charged atoms at their ends. And so the hydrogen bonding forms when a partial negative interacts with a partial positive. And I'll give you a clue. When you see a dotted line, that usually indicates a hydrogen bond, right? So if we wanted to draw another water here, we would draw it like that. That's our hydrogen bond. We could do another one. Notice these lines are polar covalent bonds. The dotted are hydrogen bonds. So polar covalent, hydrogen. All right, so if you look at a water, so this is water blown up really big. I'm sorry, I've got some weird boxy things, but this is partial negative. These are partial positive. Remember, holding this together, covalent, polar covalent, hydrogen bond here, going from the partial positive in the H and the partial negative there, right? And you can see lots and lots and lots of hydrogen bonding. So water molecules have a lot of hydrogen bonding. Again, very weak, collectively gets much stronger. So here are some questions that we'll try to go over in class as a review, but you should do these. So hydrogen bonds are attractive forces between polar molecules, comparatively very weak in comparison to covalent bonds and even ionic bonds, but collectively quite strong. And what we're going to see is that there are a lot of hydrogen bonding in DNA. So if you have DNA, there's 2 strands of DNA that are bound together through hydrogen bonding. So all along the middle of a DNA molecule, you have hydrogen bonds that are keeping the 2 strands of DNA together, right? And those are usually between, I think that they're between H's and N's, the nitrogenous base of DNA. But we'll get there, don't worry. Notice, got some good videos here. You should check them out. So hydrogen bonding is, like I said, not only between O's and H's. So again, if we look in here at this DNA molecule, and we're going to go lots into the structure of DNA. Ooh, my iPad. But you can see these hydrogen bonds. So notice when you see these dotted lines, that's indicating a hydrogen bond. So between T and A, there's 2, 3, 3, 2. So depending on what nucleotide or which part of the DNA, you can get 2 hydrogen bonds or 3. So here we have the hydrogen bond between H's and N's or H's and O's, depending on which molecule you're talking about. All right, so we have some practice questions, which we're gonna go over in class. All right, and that's where we're gonna end. We'll start next time with water and the importance of water. Bye.